Okay, so we're diving into some really cool research today, and I'm super excited about this one. You know how we've been talking about graph neural networks and all the amazing things they could do? Well, this is taking it to a whole new level. We're looking at how GNNs can actually learn to solve one of the most fundamental problems in networks, finding the shortest paths.
Yeah, and what's really blown my mind is that these networks can figure out these paths even in graphs they've never seen before. Like it's not just memorizing, it's really learning some deeper principle.
Exactly. And the research we're diving into today focuses specifically on a type of GNN called a min-aggregation GNN, or they shorten it to min-ag GNN. It's pretty amazing how these min-ag GNNs are tackling these shortest path problems.
Totally. And our mission today, I guess you could say, is to uncover what makes these MinEg GNNs so innovative and how they actually achieve this incredible learning and generalization. We want to highlight those key aha moments, the insights that make you like, oh, wow, that's how they cracked it.
Right. And to do that, we need to start with the classic approach to finding shortest paths, the Bellman-Ford algorithm. Now, this algorithm has been around for ages, so why is it relevant to this cutting-edge neural network research?
Well, it's all about inspiration. The Bellman-Ford algorithm lays the groundwork. It provides a really solid foundation for understanding how to approach the problem of finding shortest paths. And the key here is that the researchers are essentially trying to get the GNN to like mimic the steps of this classic algorithm.
So the GNN is sort of emulating this old school approach. That's pretty cool.
It is, and the way Bellman-Ford works is by repeatedly refining its estimates of the shortest distances between nodes in a network. It's this iterative process. It starts with an initial guess, basically, zero distance from the starting point to itself and infinite distance to all other points, and then step by step, it looks at all the connections and it tries to find shorter routes.
So it's like constantly checking and rechecking, looking for shortcuts until it can't find any better paths. And that's what the GNN is trying to replicate.
Precisely, and the heart of this replication lies in the architecture of the MinAg GNN. Now, I know the paper gets into some pretty heavy math, but let's stick to the big picture here. Think of it as a neural network specifically designed to work with those connections within a graph.
Okay, so it's built to understand these relationships between nodes.
Exactly. And it does this in layers. In each layer, every single node updates its knowledge of the network based on what its immediate neighbors are telling it, and of course, the properties of the connections between them, those edges.
Okay, so each node is gathering info from its buddies and updating its worldview?
Exactly. And the key part here is the minag part, that minimum aggregation.
Right, that sounds important.
It is. So during these updates, each node is getting information from all its neighbors, right?
Right.
And the network processes this info along with the edge connecting them. These edges, they're like the roads between nodes, and they have costs or weights, sort of like distances. Then comes the cool part. The node looks at all this process information from its neighbors and picks the smallest value.
It's going for the cheapest route.
Yeah, and that minimum value, along with the node's own previous understanding, is used to update the node's representation for the next layer of processing. So it's like the node is saying, all right, based on what my neighbors are telling me, what's the absolute shortest, most efficient way to get to where I need to go?
So it's constantly looking for shortcuts based on what its neighbors have figured out. But how does all this lead to actually learning the shortest paths, not just finding them in a specific case? That's the mind-blowing part, right?
You got it. And this is where the idea of algorithmic alignment comes in. The breakthrough here is that the researchers designed the GNN's architecture to specifically mirror the steps of Bellman-Ford. That mine aggregation step we were talking about, where it picks the smallest value, is basically like Bellman-Ford's core move, finding the shortest distance by checking all possible one-hop extensions from its neighbors. It's not just doing something with the graph, it's actually executing this classic shortest path logic, but in a neural way.
So they built the network to think like the algorithm, which is super clever.
It is, right. And to kickstart this process, the initial state on the network has to be just right.
Makes sense. You got to give it the right starting point.
Exactly. And the initial representations of the nodes, how we set those up, is super important. For shortest path problems, we usually give the starting node a value of 0, meaning it's 0 distance from itself.
It's home base.
Exactly. And all other nodes, they'll start with a super high value, something like infinity. Think of it as saying that initially, we assume all nodes are infinitely far away from the starting point, except for the starting point itself.
It's like saying, we have no clue how far away anything else is yet.
Precisely. That sets the stage for the GNN to start its iterative exploration.
Okay, so we've set the stage, given it the starting point and the infinite distances. Now, the research also dives into a very simple version of this, just a one-layer MinAg GNN. Why focus on something so basic?
Well, it's a classic strategy in research. You start simple to really understand the core mechanisms at play. This one-layer model, it just does one update step, one iteration. And by analyzing this bare bones model, the researchers can clearly isolate and demonstrate the fundamental principles.
So it's like a proof of concept.
You could say that. And what's really neat is that even with this one-layer model, they were able to train it on a super limited set of simple graphs.
What kind of graphs?
Just like paths, a line of nodes. And the goal was to see if this basic GNN could learn to perform a single step of the Bellman-Ford update.
So it's like teaching it the basic rule, look at your neighbors and see if you can get closer to the target.
Exactly. And this brings us to another big idea from the research, sparsity.
Sparsity, that sounds familiar.
Yeah, we've talked about it before in other contexts, but here it plays a crucial role in helping these GNNs generalize well. It's all about making the network think lean, so to speak.
So fewer connections, right?
Exactly. By encouraging the network to have fewer connections, it learns a strategy that isn't tied to the specifics of those simple training graphs. That means it can handle a much more complex graphs it's never seen before.
Okay, so sparsity makes it more adaptable, more flexible. But how do they actually encourage this sparsity during training?
They use a technique called L1 regularization. Don't worry too much about the name, but basically it's a way to mathematically push the network to reduce the strength of many of its connections. Think of it like pruning a tree. You're getting rid of unnecessary branches.
So you're streamlining it.
Exactly. And the research showed that when they used this L1 regularization, those networks not only had way more zero-valued connections, like those connections were essentially turned off, but they also performed way better on those unseen graphs.
It's like getting rid of distractions helps it focus on the essentials.
That's a great way to think about it. And what's even more impressive is that in a two-layer sparse GNN, when they trained it to perform two Bellman-Ford steps, the connection strengths converged to specific values that were directly linked to the edge weights in the graph. For example, they saw connection strengths in the first layer settle around a value A, and then in the second layer, it became 1A, which is precisely how you'd use edge weights in a two-step Bellman-Ford calculation.
Wow, so it's like the network is literally learning the mathematical relationships encoded in the algorithm.
It really does seem that way. It's strong evidence that the network is actually implementing the algorithm in this distributed neural way.
That's awesome. Now, I'm guessing all of this empirical work is backed by some solid theoretical foundation, right?
Oh, absolutely. And that's where Theorem 2.3 comes in. Actually, there's a more detailed version, Theorem C.20, but they both essentially provide the theoretical guarantees for the GNN's ability to learn and generalize these shortest paths.
Okay, so they're not just saying, hey, it works, they're showing why it works mathematically.
Exactly. What the theorem basically says is that if a MINAG GNN achieves a low training error on a specific set of well-chosen examples, and we keep those connection strengths sparse using regularization, then it can correctly carry out a certain number of Bellman-Ford steps, even on completely new graphs it's never encountered before.
So with good training and sparsity, we can trust it to perform well even in uncharted territory.
That's the idea. And the cool part is that the theorem also shows that the potential error in how well it performs is actually mathematically bounded. It depends on how well it did during training.
So the better it learns during training, the more reliable it'll be on those new graphs.
Yes. And to get the strongest guarantees, the theorem suggests that the training data should be specifically designed to cover examples that require a particular number of Bellman-Ford steps.
So you need to train it on tasks that reflect the level of complexity you want it to handle in the real world.
Precisely. And speaking of complexity, the research also explores the question of how complex these networks actually need to be, particularly how many layers they need.
So how deep does this rabbit hole go?
Yeah, and Lemma C.14 tackles that question head on. Basically, what it proves is that if you have a MINAG GNN with fewer layers than a certain number of Bellman-Ford steps, it can't perfectly solve shortest path problems that require that many steps.
So if the path needs 5 steps, your network needs at least 5 layers.
Exactly. The network needs to have enough depth, meaning enough layers, to allow information to flow across the graph to properly mirror the number of steps needed in the algorithm. It's like trying to solve a 5-step puzzle with only 3 moves. It's just not enough.
So the network's complexity needs to match the complexity of the problem it's trying to solve. That makes sense.
Right. You can't expect a shallow network to capture a process that requires a bunch of sequential computations. They also looked at a specific type of GNN called path-derived GNNs and pointed out some of their inherent limitations.
Like what?
Well, lemmas like C.16 and corollary C.19 show that sometimes, especially with very simple graphs like those paths we talked about, the network's output might become insensitive to changes in the costs of those connections, those edges.
So it might not be able to tell the difference between a cheap path and an expensive one.
Exactly. It's like it loses the ability to differentiate. And this suggests that if we're not careful about how we design and train these networks, they might miss some crucial information.
It's a reminder that the architecture alone isn't enough. You need the right training and data too, but of course, this research isn't all just theory. They actually put all these ideas to the test, right?
Oh, absolutely. They have a whole second on experiments where they really get their hands dirty and see how these MinAd GNNs perform in practice.
And what do they find?
Well, one of the most exciting findings was that training models with that L1 regularization we talked about, that sparsity-inducing technique, consistently resulted in lower error rates on those unseen graphs compared to models trained without it.
So sparsity really does make a difference.
Yes, it's not just a theoretical concept. And what's even more exciting is that those connection strengths in the regularized models actually converge to those specific sparse patterns that their theoretical analysis predicted. You know, those patterns that we were talking about that correspond to an efficient Bellman-Ford implementation.
So the theory and the real-world results actually line up. That's always great to see in research.
It is. And it gives us even more confidence that these networks are truly learning the underlying algorithmic logic, not just memorizing the training data. Oh, and they even found that even when they intentionally designed the network to have fewer connections than might be ideal, that L1 regularization still helped it learn a surprisingly effective representation.
So even when it's a bit handicapped, sparsity still gives it an edge.
Exactly. It's like it forces the network to be super resourceful and figure out how to make the most of what it have.
That's awesome. So just to wrap things up, what are the biggest takeaways from this research? What are those aha moments that really highlight what's new and innovative here?
Well, I think the biggest aha moment is the idea of algorithmic alignment. This notion that we can design neural networks to mimic the steps of well-established algorithms like Bellman-Ford.
So it's about leveraging the power of existing knowledge and embedding it into these networks.
Exactly. And the second big aha is the crucial role of sparsity in achieving generalization. Using techniques like L1 regularization, we can encourage these networks to learn lean, efficient representations that aren't overly specific to the training data, allowing them to tackle new, unseen graphs with remarkable accuracy.
So algorithmic alignment plus sparsity equals a recipe for robust GNNs that can truly generalize.
Precisely. And this combination allows the GNN to go beyond just memorizing patterns and actually learn the underlying logic of the algorithm.
And why is this such a significant development for the field of graph learning? Why should people care about this?
Well, it addresses one of the biggest challenges in GNN research, out-of-distribution generalization. Traditionally, models that perform well on the data they're trained on often fall apart when faced with new types of graphs.
Like they're overfitting to the training data.
Exactly. But this research offers a potential solution to that problem. By embedding the structure of these known algorithms within the neural network itself and encouraging the learning of sparse, efficient representations, we might be able to overcome this generalization barrier and build GNNs that are much more robust and reliable in real-world applications.
So it's a big step towards building GNNs that can handle the complexities and uncertainties of the real world, not just perform well in controlled lab settings.
Exactly. And that opened up a world of possibilities.
It really does. It makes you think about all the potential applications of these ideas in other domains where graphs are everywhere.
Oh, absolutely. And that's something I'd love for our listeners to ponder. Could we apply these same principles of algorithmic alignment and sparsity to other graph-based problems? What about recommendation systems, for example, which can be viewed as graphs connecting users and items? Or what about computational biology, where we're analyzing those complex protein interaction networks? Or even in understanding the dynamics of social networks, the possibilities are endless.
It's like this research has opened a door to a whole new way of thinking about how to build powerful and generalizable AI systems.
It has, and I think we're just scratching the surface of what's possible.
Well, this has been a fantastic deep dive. Thanks for sharing your expertise and breaking down these complex ideas in such a clear and engaging way.
You're welcome. It's always a pleasure to talk about this fascinating stuff.
And to our listeners, keep exploring, keep questioning, and keep pushing the boundaries of what's possible with AI. Until next time.